Hello students, welcome to the class on multivariable calculus and geometry. In this class, we will study two theorems related to linear transformations of a vector space. We know the notation L of xy. The space L of xy is the set of all linear transformations of the vector space x into the vector space y. We have proved that L of xy forms a vector space with respect to the addition and scalar multiplication of linear transformations, and we have defined a norm for an element A belongs to L of Rn Rm. The norm is defined by norm of A is equal to supremum of modulus of A of x, where x belongs to Rn with mod x less than or equal to 1. Now, this is our first theorem. If A belongs to L of Rn Rm, that is, A is a linear transformation from the vector space R power n to the vector space R power m, then first we have to prove norm of A is less than infinity, that is, norm of A is a finite real number, and A is a uniformly continuous mapping of R power n into R power m. And secondly, if A and B are elements of L of Rn Rm and C is a scalar, then norm of A plus B is less than or equal to norm of A plus norm of B, and norm of CA is equal to mod C into norm of A, with the distance between A and B is defined as norm of A minus B. L of Rn Rm is a metric space. Also, if A belongs to L of Rn Rm and B belongs to L of Rm Rk, then norm of BA is less than or equal to norm of B into norm of A. So, in the first part, we have to prove that if A is a linear transformation from R power n to R power m, norm of A is finite. We know that norm of A is equal to supreme of modulus of A of x, where x belongs to R power n with mod x less than or equal to 1. Now, we know the standard basis for R power n, that is denoted by E1, E2, etc. En, where Ej is an n-tuple whose jth entry is 1 and all other entries are equal to 0. Now, let x be an element of R power n with mod x less than or equal to 1. Then, since this E1, E2, etc. En is a standard basis for R power n, any element of R power n can be uniquely represented as a linear combination of these basis elements. So, the vector x has a representation of the form x is equal to sigma I varies from 1 to n some Ci into Ei, where Ci's are unique scalars. Now, this x satisfies the condition mod x less than or equal to 1. So, mod x less than or equal to 1 implies modulus of sigma I varies from 1 to n Ci into Ei less than or equal to 1. And we know that modulus of summation is less than or equal to summation modulus. So, sigma I varies from 1 to n modulus of Ci Ei less than or equal to 1. This implies sigma I varies from 1 to n mod Ci into mod Ei less than or equal to 1. And we know that mod Ei is equal to 1 for every I is equal to 1 to etc. n. So, this implies sigma I varies from 1 to n mod Ci less than or equal to 1. Now we have mod A of x is equal to modulus of A of, we substitute for x, and this is equal to modulus of Since A is a linear transformation, A of sigma Ci Ei is equal to sigma Ci into A of Ei. Now, modulus of summation is again less than or equal to summation modulus. So, this is less than or equal to sigma I varies from 1 to n modulus of Ci into A of Ei, which is equal to mod Ci into mod A of Ei. So, we get mod A of x is less than or equal to, we know that mod Ci is less than or equal to 1 for each I is equal to 1 to etc. n. So, this term is always less than or equal to 1. So, we have mod A of x is less than or equal to sigma I varies from 1 to n mod A of Ei. Now, we have norm of A is equal to supremum of modulus of A of x, where x belongs to R power n with mod x less than or equal to 1. Now, modulus of A of x is less than or equal to this summation. Therefore, here x, the vector x satisfies the condition mod x less than or equal to 1. Therefore, the supremum of this collection is also less than or equal to this quantity. That is sigma I varies from 1 to n modulus of A of Ei. And what is A? A is an element of L of Rn Rm. That is, A is from Rn to Rm. A is a linear transformation from R power n to R power m. So, A of Ei is an element of R power m. Therefore, modulus of A of Ei is finite, and therefore this is a finite summation. So, this term is also finite. That means norm of A is finite. Next, we have to prove that the linear transformation A from R power n into R power m is uniformly continuous. In order to prove this transformation is uniformly continuous, we use Lipschitz condition. That is, we consider any two elements from the domain, that is R power n. So, let x and y belongs to R power n. Then we consider modulus of Ax minus Ay, and it is equal to modulus of A is a linear transformation. So, this is equal to A of x minus y. And we have proved that modulus of A of x is less than or equal to norm of A into mod x. So, modulus of A of x minus y is less than or equal to norm of A into mod x minus y. And this is true for every x and y element of R power n. So, the linear transformation A satisfies the Lipschitz condition or the Lipschitz inequality. So, this transformation A is uniformly continuous. In the B part, we have to prove that if A and B are linear transformations from R power m to R power n, if A and B are linear transformations from R power n to R power m, we have to prove norm of A plus B is less than or equal to norm of A plus norm of B. So, in order to prove that, we consider any vector x of R power n with mod x less than or equal to 1. Then we consider modulus of A plus B of x, and it is equal to A and B are linear transformations. So, it is equal to A plus B of x is defined by A of x plus B of x, and which is less than or equal to modulus of A of x plus B of x is less than or equal to modulus of A of x plus modulus of B of x. And since these two are linear transformations, modulus of A of x is less than or equal to norm of A into mod x. Similarly, modulus of B of x is less than or equal to norm of B into mod x. So, from this we can take mod x outside. So, this becomes norm of A plus norm of B into mod x. Now, by definition, norm of A plus B is equal to supreme of modulus of A plus B of x, where x belongs to R power n satisfies mod x less than or equal to 1. And we have proved that modulus of A plus B of x is less than or equal to norm of A plus norm of B into mod x. So, the supremum of this collection is also less than or equal to supreme of norm of A plus norm of B into mod x, where x in R power n with mod x less than or equal to 1. Since mod x less than or equal to 1, this term is less than or equal to norm of A plus norm of B. So, supreme of this collection is less than or equal to norm of A plus norm of B. So, we proved that norm of A plus B is less than or equal to norm of A plus norm of B. Next, we have to prove that if A is a linear transformation from R power n to R power m and C is any scalar, then norm of CA is equal to mod C into norm of A. So, first we consider modulus of CA of x, and it is equal to this operation is defined by C into A of x. So, modulus of C into A of x, and it is equal to mod C into mod A of x. And we have norm of CA is equal to, by definition, it is supremum of modulus of CA of x, where x belongs to R power n and mod x less than or equal to 1. And we substitute for this term. And this is equal to mod C into mod AX. So, supreme of mod C into mod AX, where x belongs to R power n with mod x less than or equal to 1. Now, this mod C, it is independent of x. So, we can take this term outside. So, mod C into supreme of this. And this is nothing but norm of A. So, we have norm of CA is equal to mod C into norm of A. Next, we have to prove that the vector space L of R power n, R power m is a metric space with the distance between two elements A and B in this space is defined by norm of A minus B. So, in order to prove that this L of R power n, R power m is a metric space, we have to prove this distance function satisfies all the properties of a metric. The first property is non-negativity, and so we consider norm of A minus B. We know that norm is defined in terms of supremum of modulus of some absolute values. So, from the definition itself, it is clear that norm of A minus B is greater than or equal to 0, and also norm of A minus B is equal to 0 if and only if A is equal to B. And we have norm of A minus B is equal to norm of B minus A. And these properties are very easy to verify, because norm here is defined in terms of modulus function, and it is symmetric and non-negative, and we know mod x equal to 0 if and only if x equal to 0. So, applying all these properties, we can easily verify all these conditions of metric. So, it remains to prove only the triangle inequality. That is, we consider three elements from this vector space L of Rn, Rm. So, we consider three linear transformations A, B and C. We have to prove that norm of A minus C is less than or equal to norm of A minus B plus norm of B minus C. That is, distance between A and C is less than or equal to distance between A and B plus distance between B and C. So, consider norm of A minus C, that is equal to norm of A minus B plus B minus C. That is equal to, or this is less than or equal to, we have proved that norm of A plus B is less than or equal to norm of A plus norm of B. So, applying that property, this is less than or equal to norm of A minus B plus norm of B minus C. So, this is our triangle inequality. So, here the distance function defined by norm of A minus B satisfies all the properties of a metric. So, we can conclude that the vector space L of Rn, Rm is a metric space. Now, in the last part of this theorem, we have to prove if A is a linear transformation from R power n to R power m and B is a linear transformation from R power m to R power k, then norm of BA is less than or equal to norm of B into norm of A. So, first we consider the composition BA. It is well defined. Now, modulus of BA of x, that is equal to modulus of, this is composition, so it is equal to B of A of x. And so, it is less than or equal to, and since B is a linear transformation from R power m to R power k, modulus of B of a vector, this A of x belongs to, here x belongs to R power n, so A of x belongs to R power m, so B of A of x, that is B of a vector of R power m. So modulus of B of A of x is less than or equal to norm of B into modulus of A of x. We have proved this property in the previous class. So again, this modulus of x is less than or equal to norm of A into norm x. So we have modulus of BA of x is less than or equal to norm of B into norm of A into mod x. Now we take the supremum on both sides. Supremum is taken over all x belongs to R power n with mod x less than or equal to 1. So taking the supremum on both sides, what we get? What is the supremum of modulus of BA of x where x belongs to R power n with mod x less than or equal to 1? Its supremum is nothing but norm of BA. And taking this supremum, we get, that is supremum of norm of B into norm of A into mod x where x belongs to R power n with mod x less than or equal to 1. So we will get this also less than or equal to norm of B into norm of A. So we proved that norm of BA is less than or equal to norm of B into norm of A. So in this theorem we proved that L of R power n R power m is a metric space. So since this is a metric space, we can define several concepts in metric space like open set, closed set, limit point, continuity, etc. for this space also. Now our next theorem, theorem number 9.8. Let omega be the set of all invertible linear operators on R power n. Then first part, if A belongs to omega and B belongs to L of R power n, that means B is a linear operator on R power n, and norm of B minus A into norm of A inverse is less than 1, then B belongs to omega. So what is omega? Omega is the set of all invertible linear operators on R power n. And if A belongs to omega and B is any linear operator on R power n and norm of B minus A into norm of A inverse is less than 1, then we have to prove B belongs to omega, that is B is invertible. Now the second property, omega is an open subset of L of R power n. Omega is an open subset of L of R power n. And the mapping A goes to A inverse is continuous on omega. So we have to prove this collection of all invertible linear operators on R power n is an open subset of L of R power n, and this mapping, that is A is mapped to its inverse, A inverse, is continuous on omega. So in the statement we are given that A is invertible. So norm of A inverse, that will be a real number. So let us take it as some 1 by alpha, and let norm of B minus A is equal to some beta. Then we are given this condition, norm of B minus A into norm of A inverse is less than 1. So from this what we get, norm of B minus A, that is beta, into norm of A inverse, that is 1 by alpha. So beta by alpha is less than 1 implies beta is less than alpha. Now first of all we have to prove that the linear operator B is invertible. That is to prove B is 1 to 1 and onto. And in order to prove B is 1 to 1, we will prove that the null space of B contains the 0 vector only. That is our method. So let us consider any vector R, x from the space R power n. and we consider alpha into mod x. Now mod x can be written as I of x, where I is the identity operator, which is a linear operator. Now since we are given A is invertible and its inverse is denoted by A inverse, this I can be replaced as A inverse into A. So alpha into modulus of A inverse into AX, and it is less than or equal to, since A inverse is also a linear operator, this is less than or equal to norm of A inverse into modulus of A of x. Now what is norm of A inverse? That is 1 by alpha. So alpha into 1 by alpha, that is equal to 1. So this term will become modulus of AX. So this is equal to modulus of AX, and it can be written as modulus of AX minus BX plus BX, and this is less than or equal to modulus of AX minus BX plus mod BX, and modulus of AX minus BX, that is modulus of A minus B of x plus mod BX, and this is less than or equal to norm of A minus B into mod x plus mod BX. And we have norm of B minus A is equal to beta, and norm of B minus A is the same as norm of A minus B. So this is beta into mod x plus modulus of Bx. So we proved that alpha into mod x is less than or equal to beta into mod x plus modulus of Bx. So taking this term onto the left side, we will get alpha minus beta into mod x is less than or equal to modulus of Bx for every x belongs to R power n, and we have beta is less than alpha. So alpha minus beta is always greater than 0. So this term is always positive, and here we have mod x and here we have modulus of Bx. So the terms on the right side and left side of this inequality are all positive. This means that mod Bx equal to 0 only when mod x equal to 0, that is when x equal to 0. So we have Bx equal to 0 if and only if x equal to 0. That means Bx is not equal to 0 only when x not equal to 0. Okay. So if x not equal to 0, Bx not equal to 0. So that means B is a 1-to-1 map. So B is a linear operator which is 1-to-1, and it is defined on R power n. R power n is a finite dimensional space. We know dimension of R power n is equal to n. So by theorem 9.5, we will get range of B is equal to the whole R power n, that is B, the linear operator B is onto. So B is 1-to-1 and onto, that means B is invertible. That means B belongs to omega, the set of all invertible linear operators on the space R power n. So in the first part we proved that if we are given an invertible linear operator A, then we proved that there exists B also belongs to omega, such that A and B satisfies this condition. Norm of B minus A is less than 1 by norm of A inverse, and this 1 by norm of A inverse is equal to alpha. That is, corresponding to any element A from the set omega, we have a positive real number alpha, such that there exists one B belongs to omega with norm of B minus A is less than alpha. That is, distance between A and B is less than alpha. This means that the element B belongs to the open ball centered at A and radius alpha. So corresponding to every element A in omega, there exists a positive real number alpha and an element beta in omega, such that element B in omega, such that B belongs to the open ball centered at A and radius alpha. So by definition, this omega is an open set. So this omega is an open subset of the set of all linear operators defined on R power n, that is L of R power n. Next, we have to prove that the mapping A goes to A inverse is continuous on omega. So, for that we replace x by B inverse y in 1. This is our inequality number 1. Alpha minus beta into mod x less than equal to modulus of bx. This is true for every x belongs to R power n. In particular, this holds for the vector B inverse y also, because B is a linear operator on R power n. So, B inverse y again belongs to R power n. So, substituting for x here, we get alpha minus beta into modulus of B inverse of y is less than equal to modulus of bx, that is B into B inverse of y, and B into B inverse equal to identity operator. So, this becomes modulus of y, where y belongs to R power n. So, we have modulus of B inverse y is less than or equal to 1 by alpha minus beta into mod y. So, norm of B inverse, that's equal to, by definition it is supremum of modulus of B inverse of y, where y belongs to R power n with mod y less than equal to 1. And we have modulus of B inverse of y is less than equal to alpha minus beta the whole inverse into mod y. So, taking supremum over all y belongs to R power n with this condition mod y less than equal to 1, we will get this is less than or equal to alpha minus beta the whole inverse. Now, we know that B inverse minus A inverse is equal to B inverse into A minus B into A inverse. Now, multiplying this, we get B inverse into A inverse, that is B inverse. First time B inverse. Then second time is B inverse into B into A inverse. So, that is A inverse. So, we have B inverse minus A inverse. Now, consider norm of B inverse minus A inverse, that is equal to norm of this. And it is less than equal to, we know norm of AB less than equal to norm of A into norm of B. So, this is less than equal to norm of B inverse into norm of A minus B into norm of A inverse. And norm of B inverse is less than equal to alpha minus beta the whole raised to minus 1. Norm of A minus B, that is equal to norm of B minus A, and it is our beta, and norm of A inverse is 1 by alpha. So, substituting, we get this RHS is equal to beta by alpha into alpha minus beta. Now, as beta tends to 0, what happens? As beta tends to 0, the RHS tends to 0. That means, norm of B inverse minus A inverse tends to 0. Now, what is beta? Beta is equal to norm of B minus A. So, norm of B minus A tends to 0 implies norm of B inverse minus A inverse tends to 0. This means that the mapping A goes to A inverse is continuous. So, we discussed two theorems in this class, and these two theorems are very important. So, study well. Thank you.